In this third installment on the center mass, we're going to look at how doing the center mass can make a very complicated problem with complicated graphs into a simpler problem with simpler graphs. So for instance, in this case we have a box, and the box has a mass m, and the box is initially stationary, and inside we have a ball, and a ball that is traveling with some velocity v. Now we're going to be asked to graph the position of the ball as a function of time, the position of the box as a function of time, and the position of the center of mass. So for the ball's initially going in v, so we know some things. We know that it has a slope, for instance on its position time graph, of v. It's a straight line graph because it's moving at constant velocity to the right, and we know that it initially starts roughly at x equals 0. So putting that in, we have something that looks like that. It goes for a distance until it gets to 2L. And we can even determine that time. For instance, we know that v is equal to the distance it covers, 2L over time t. So t is equal to 2L over v. So let me put that in there. So this would be till time 2L over v. Likewise, we know that for the box initially has a location. We call that the center, say, of this box. That would be right about here in the middle at x equal L. So the box starts at x equal L. There's L. And it stays at a constant velocity, which is of 0. It's at rest, so it goes over to, for a time, 2L over v. So it has a slope of 0. It's a horizontal line. Now, at that point, the ball gets over here and hits right there against the wall. And at that point, it undergoes an elastic collision, and in that collision, the ball stops and the box takes off. So now the box is moving at a velocity v. So we still have momentum mv, capital M times v, where m is the mass of the box, and the ball has no velocity because it stopped. This was made to make this problem easier by making the two boxes have the same mass, the ball and the box. Otherwise you'd have to actually work out conservation of linear momentum for that. So at this point, the ball goes over for exactly the same amount of time. So this would now be 4L over v. And this goes up here till it gets to, if I've drawn this right, to 3L. And this would be 4L over v. At that point, the back end of the box then comes up and smacks into the ball. The ball takes off, and the box stops. So at this point, we get this, and we get slow v again. So this is the x of the ball, and this is the momentum, the position of the box. Now if you look at those, neither one of those graphs is extremely easy. They're not real hard. We can, like I said, at every point find the velocity. This is the slope is v. Here the slope was 0, so it was not moving. Here it's moving at constant velocity. And likewise we could do the same thing over here. But it's not something like the equation of a straight line or something. Let's look at the center of mass now. The center of mass says that you replace this complicated two object system with a single object located at the center mass. Now if this was one ball of mass m representing the box, and this is the other ball right there, the center mass is halfway between them. You can compute this, or you can just note by symmetry that that's so. Halfway between them, if this is L, would mean that it starts at L over 4. So we'll go down here and make that notation on the center mass graph. So it starts at I'm sorry, not L over 4, but L over 2. Get that right. Okay, this distance here was L. This distance was 0, halfway between it's L over 2. Also, the total linear momentum has to be the same. We've replaced this whole thing with a single ball. So I've got this single ball of mass 2m moving at some new v center mass located at L over 2 initially, and its total momentum has to stay the same as the total momentum of the individual system. So I have the 2 times the mass, that being the mass of the ball, times the center mass, has to equal the momentum of the individual parts. This was m times v plus m times 0. So 2m v center mass has to equal mv. I'll kill the m's. So center mass moves at v over 2. Now here's the thing. Since it's a single ball, there is no interaction now between the parts. It's just one object. It has that speed. There's nothing else slowing it down as it moves around because there are no external forces. The linear momentum of the system is conserved, while the linear momentum of the individual parts is not. So its graph simply looks like this. Slope equal v over 2. It's a straight line. It's relatively easy to write the formula for the center mass. It would be v over 2 times t, plus it started initially at L over 2. Constant speed in a straight line. Obeying Newton's first law. It was not so easy to describe the ball or the box because of the interaction when they hit and collide. If we describe the system, though, with the center mass, we'd find that the whole box plus the ball moves at a constant rate across the floor. In fact, they make toys based on this idea. You may have seen these like rolling toys, which have something inside that makes it appear, since you're only seeing the box, that they jump, start, and move around. And you can get cats or other things to play with them. Sometimes they'll put a raccoon tail on the end of these little bouncing balls that they have. But it's really just two objects, an outer ball that you see, and something on the inside that's moving around, sharing energy and momentum between the system. If you looked at it from the center mass, it would be a very simple system. So engineers and physicists often take complicated systems like colliding particles at CERN at the Giant Collider, and they don't analyze them from what's called the lab frame, where you're watching the particle run to the end and smash into something. They analyze it from the center of mass frame. That is, they look at this and in fact maybe put their axis on the center mass. If they put their axis on the center mass, then the center mass is at rest. And so it doesn't appear that the particle flies down the end of the beamline, for instance, and maybe strikes a stationary target. It looks like the target and the ball come at each other. So let me kind of draw you a picture of that. So you could have a target, and you could shoot a bullet or a ion beam at it like this. That's called the lab frame. But when they often do calculations to make the math simpler, they will have this moving with some velocity, and they'll have the target moving back with some velocity, such that the center mass is stationary. This is called the center of mass frame. And many things in physics are easier to analyze that way. So this is kind of a aside. So the center mass is an important thing. You don't get asked a lot of questions usually to solve and such, but you should at least be aware of the concept, and we'll certainly need it in putting axis at the center mass when we're doing axis of rotation in our moment of inertia calculations later in the course. So that completes this section on the center of mass.